is extremely energy dense, very stable at ambient temperatures and pressures, very transportable, very available. There were times when people thought they were running out of oil and gas. There is no danger of running out of oil and gas. There's a lot of it, and fairly easy to exploit, and we know how to exploit it. So when you're thinking in economic terms about finding an alternative, you're up against a really tough competitor, and a lot of it, and it's embedded in everything, everything we do. So the size of the task is monumental. And the time now to 2050, when you're thinking about the sort of projects that we're used to doing in oil and gas, is very short. A project to new LNG carrier, or here we're talking new hydrogen projects. These are 10-year projects. From the moment of idea, and when you're thinking that you also need to, you've got some things that are TRL, very low, then these are things where every decade counts. And you haven't even got 3 decades. You've only got so I think partly in the experience of what we've been doing in hydrogen, but also the experience from oil and gas, you realise that the size of the task is absolutely monumental. And I think as we're thinking in terms of new technology, R&D ideas, how do you have to bear that in mind, in that you've got to be able to try things, roll your sleeves up, try things, and kill them quickly. Move on quickly. That you can't. You can't waste a decade doing the wrong thing. And I've seen this, it hit home. There's a guy from Ørsted, who's a big offshore wind company. They big project plans, the east coast of the US for large offshore wind installation. 5 years on, between the regulatory challenges, the pricing, the business model, they had to kill the project. And the guy spoke, there was a panel with me recently, enormously frustrated, because he said, I had 3 decades, I've just wasted the first one. And I can't do that again. I cannot waste another decade. So I think, this size of the task is I'm going to talk some more about these, but I think when you start to produce, you start to work on electrolyzed for hydrogen. You'll see on the picture here, so this is the first electrolytic stack that we produced. With the pilot line that we set up. So this is solid oxide electrolysis. I don't know how familiar you are with electrolysis, but essentially you've got 2 different types of electrolyzer that exist today, PEM and alkaline. You're essentially taking water, H2O in, you're using electricity and electrochemical cell to split it into your sort of hydrogen and oxygen. Both PEM and alkaline electrolyzers take in water. And obviously split into hydrogen and oxygen. What you're interested in an electrolyzer is how much electricity does it consume per kilogram of hydrogen that you produce. Essentially a kilogram of hydrogen contains sort of 33 kilowatt hours, if you like, of useful energy. You're desperately trying to use as little electricity as possible to produce that. And when you think about the cost of that kilogram of hydrogen that you produce, 75% of the cost is the cost of the electricity going in. So electrical efficiency is a big game changer. And of course, the bigger you get, and you need to be at scale, then the more impact it has to get that electrical efficiency up and the useful electricity down. The electrolyzer we were building is a high temperature electrolyzer, so it's a solid oxide electrolytic cell. High temperature means that the reaction happens at 700-800 degrees, and that you put steam in. So essentially, you're getting a boost in electrical efficiency that could be sort of 20 to 30% in a lab. You've got to find the story when you obviously do it in the real world in a demonstration project. But the reason that we were pursuing this type of electrolyzer was to get greater electrical efficiency, but largely by being able to use industrial heat to replace electricity consumption. So where it's interesting is where electricity is expensive, which it is a lot of the time, and you have access to cheaper industrial waste heat, if you like. So I'm going to go on and talk a little bit about the context. Let me and then the other things that we've learned. So I told you a bit about Schlumberger, now called SLB, global technology company, really trying to drive energy innovation and thinking. had a rebranding exercise a couple of years ago, and it's really resonated, this idea of how do you think about a balanced planet? How do you need to think about, you know, oil and gas production, how you clean it up, you scale it back, you replace it, while also working on, you know, the solutions of the future. So we're, in terms of what characterizes the company, so set up 100 years ago. The first job was done in France, the second in Russia, and the third in the US. So it's an extremely international company. We've got technology centers all over the world. And what's been interesting is that for the last 40 years, the strategy of the company has been to recruit the same number of people, or thereabout, a percentage of people in each country into the workforce as we have revenue from the country. So this is just a snapshot, but it does sort of characterize a little bit the way the company's worked and how we've ended up, is that we have a nationality mix that pretty much reflects where we do business, and you can see what the, you know, the numbers look like. And that's interesting in terms of, I would say, the diversity of thought that it brings. Generally, when you're in a team of 10 people, you've got, you know, at least 8 different nationalities, and we're a highly technical company. So of the 100,000 people in the company, over 28,000 of them identify as you know, scientists, engineers, technical people that are, you know, I mean, many become managers and such, but the 28,000 are working in technical roles. So in terms of what we do, so the first part, which I'm going to talk about, is decarbonizing industry, and the driver for us in the hydrogen space, particularly with the high temperature electrolyser, was to look at industrial decarbonization. So particularly the steel industry and the cement industry, that need hydrogen, or in part, that need CCS, and that need to be thought of. And I would say this is, you know, in terms of the way you guys are thinking about things here, I think it's very relevant. You have to think of it as a sort of holistic solution, a systems problem, if you like, when you're thinking about how to decarbonize, you know, steel and cement plants. Innovating in oil and gas, scaling. So there's a big subject about how do you take innovative technologies that are going to be transformative in the new energy space and the decarbonisation space, and actually manage to make them have impact at scale, which is about manufacturing. It's about understanding, you know, the context, and then how do you find solutions that really can scale and make a large impact. And we have a, you know, sizable digital business. So I've been in the new energy space for the last 4 or 5 years. So that's carbon solutions, carbon capture, storage, a lot of geothermal. So the company knows the subsurface very well. So everything that is geothermal, which is deep geothermal, but then also geoenergy in the sense of shallower geothermal, where you might use you know, ground source heat pumps. So we've set up a business there to bring the way in which we drill in oil and gas is often directional. So you steer the wells to where you want to go. What we've started doing in a business called Celsius is applying the same sort of thinking about steered wells, if you like, to be able to increase the contact area, surface area for ground source heat pumps. So to be able to take something that is just like a car park size space in an urban environment, and rather than you know, drilling big loops for your ground source heat pump, drill wells that can enable you to bring heat pumps into quite dense urban areas. So we've transformed the office, the technology center that I work out of just outside Paris. We've transformed all the heating and cooling to ground source directionally drilled wells. So critical minerals, the way in which lithium, for example, gets extracted. When you look at it and you come from it, you look at it, it's pretty ugly. It's large evaporation pits, a lot of it, not very efficient, not very environmentally friendly, and quite costly. So we've been trying to see, in a similar way as we're thinking about ground source heat pumps, how can you apply the way that you drill for resources in a more efficient manner in oil and gas? Can you do a similar thing for lithium so that you don't actually have to bring all the brines to the surface, that you can try and optimize the process? So we've been doing that on quite a large scale in Nevada in the US. Stationary energy storage around batteries, but not only, some other much larger scale storage systems, and then hydrogen. And again, you see the same stack that I've been working on for the last 3 years. So if I jump in there, and I'll just tell you a little bit more about, so in the hydrogen space, we chose to focus on production technologies. So when we first got into this partnership, it was I was there in the very first meetings, and I brought from Schlumberger, from SLB, mechanical engineer, electrical engineers. I brought a process guy, a materials guy, and we met with folk who'd been working on a solid oxide electrolyser for the last 15 years, and we had a 2-day session in a room. And as they sort of stripped it back and tried to teach us, well, okay, this is, it was something entirely new to all of us. But at the end of the day, it's a mechanical object. Things need to flow right. It needs to be sealed. You're dealing with temperature. When you strip it, you're dealing with different material properties. So once you sort of stripped it back to fundamentals, we had expertise in the different elements, but we'd never quite spoken the same language before. So, interesting to see then. And of course, in manufacturing, you've got to manufacture these things in high volume, cheaply, and safely, and then you've got to operate in an industrial space. So we spent the last 2 or 3 years, I guess, trying to understand how can we build electrolyzers. So this, another picture of the stack. So this is a stack of electrochemical cells. So we set up a company, and I'd never done anything like this before. I think in Schlumberger we'd never done anything like this before, where we set it up as a public-private partnership. So it was essentially the company 50% owned by the National Research Establishment in France, also some ownership by the region. So the region where we had a factory, we have the factory, built the pilot line, also invested in the company. And I think when you're in this space of transition technologies, none of it happens without the right political input. None of it happens without the right policies in place. At the moment, whether it's the UK government or pretty much any other government globally, they take every pound you spend at the pump, 50 pence of it goes into the government coffers. So, clearly they have there's going to be no interest in doing any transition technologies unless policies shift. And that is not only sort of central policies, but it's also local policies. So the idea, at some point in time, you've got to have some kind of partnership with I would say, public entities of some kind. So we jumped all in and set the company up entirely as a partnership, public and private, which there's a bunch of lessons learned from that, but I'll save them for another day, which are important as well. We really were trying to go at quite fast pace, doing 3 things at once. One, pumping more money into the research lab. So we had about, we transferred a lot of people into the company to start with. The company now has about 150, but we moved about 40 staff over on day one. We have a research group of 30 that we, on top of that we fund in the research centre, the CEA in France. We started to build a manufacturing line. So you sort of realise that actually you can have a terrific prototype in a lab, but until you've brought the manufacturing team in, you really don't know if you're heading the right way in terms of manufacturability. And the other thing that was extremely important, and I will talk more about this, was actually getting into industry at the sharp end and understand, what is this use case? What are people actually going to use this electrolyser for? Are we solving the problem they have in front of them? Have they understood the problem? Do they know what they're trying to do with it? And certainly what we found, and I suspect it's not just in the hydrogen space, is that nobody was really able to articulate the problem they were trying to solve. And that makes a big difference when you're developing technology, putting a lot of research hours in, you're putting a lot of time, money, bandwidth. You really, really need to work to understand what is the problem you're trying to solve. And I think be patient. You can. There are conferences. You can go to a conference every day of the week on the hydrogen space at the moment. I think the only people making any money in hydrogen are people running conferences. And you can get lots of, rolled up numbers, the world, globally this, globally that, it's going to do this, it's going to do that. Where the rubber hits the road is, where are you going to install that piece of technology to do what? What are the constraints? Actually really having, I would say, almost, an intimate relationship with, the people who are trying to, in a cement plant, for example, which is where we spent a lot of time, they're not calling out for hydrogen, they're calling out for how do I sell a product that is decarbonized? How do I maximize my return on my quarry and work out what to do with the CO2? It's so hydrogen could be part of the solution, but until you've understood, how do I define the problem? You're unlikely to get to the right technology to solve it. So we spent a long time designing the whole system to decarbonize a part of a steel making process with the electrolyser, and similarly in the cement industry. So these are the projects that we're working on. The one that is the most advanced, and the prototype is designed. It's being installed. We've not yet run the prototype, so I'm not going to tell you that it works, because until you've done it, you really haven't done it. You don't know if it works until you really run it. Is with ArcelorMittal. So it's a rolling mill in the southern part of France that already uses hydrogen. So this was also really interesting, that we had about 10 potential demonstration projects, a lot of them greenfield sites wanting to produce e-fuels, wanting, a lot of very creative things they wanted to do. The 7 of those 10 projects were for new uses of hydrogen. Essentially, these were newcomers. They bought a big green field somewhere and they want to produce hydrogen and sell it to somebody. Now, the truth is, when you actually have to design a project, you've got to do the system design, you've got to do the engineering for it. When all they can show you is a green field and lots of good feeling, you don't have the specifications to be able to design a project. So you can't get very far when you don't know what somebody actually wants to do with the hydrogen that you want to produce. So the 3 projects or 4 projects that we progressed, in fact, the 3 that have the 2 that have progressed the most is the chemical plant here and the steel plant, and that is because they currently use hydrogen. They have steam methane reformers on site. They know what they're doing. They know how much they use. They know they know the quality. They know the flow rate. They know the space they've got. So they can actually give you what the French call a cahier de charge. They can give you a specifications document. If they can't give you a specifications document, it's very difficult to know what are you trying to design. And when you're in that early stages of a prototype, well, you do need to know, what are you actually trying to do and trying to achieve. So, and that also, the learning then from that is very interesting, because you have a baseline. You know what they currently pay for hydrogen. You know what their current flexibility is. You know what their current energy input costs are. You know how often the plant has gone down in the last 5 years, and so you can understand the problem that you're trying to solve. So we've spent a long time in this ArcelorMittal plant, and some of the things that you learn, you may be expected to learn, and frankly, a whole bunch of the things you never expected. And I firmly believe that, smart as my team were, and they're super smart, we would never have thought of the constraints that you had or the specifications that you had, in terms of, even to the point that it's only when you start to discuss a contract, and you're in the line by line and the lawyers are there and you spent days, that they say, oh, but our waste heat that you want to use for your electrolyser, well, we currently sell it to the local town to heat the swimming pool. Well, that's sort of important information to know, because actually you are then starting to say, well, I'm robbing Peter to pay Paul, and whether you're thinking economically or thinking in terms of CO2 or energy efficiency, well, robbing Peter to pay Paul doesn't sound good. So lots of, and even another example, for example, When you look at industrial plants in, and I'm sure in the UK it's the same as in France, most of these things were built 100 years ago. You know, the steel making here is from more than 100 years ago, 150 years ago probably, and the town has grown up around it. You know, the town, Sanchez-Dapché, grew up around the steel plant. And what that tells you, for one, is that there is no space. There are houses on all sides of the, and right by where we're putting the electrolyser, well, there is a house that's right just there, and the old dear I'm not being fair, I'm slightly condescending, I apologise, I shouldn't be, but you know, noise becomes it. You have limits in noise, and you do need to compress, you do need to, and suddenly you can't do that there in that perimeter, because it's going to be, so your design problem becomes one of actually, how do I reduce the noise, more than, you know, how do I make, and you make a trade-off in efficiency. I don't mind if it's more expensive, because actually I just can't put it there. The other one in the steel plant, for example, is the steel plant in the south of France. Sorry, the primary steel making plant, the blast furnace, enormous area of land around it, and you think, well, this is an easy one, I don't have the same constraint as in the rolling mill. But then you realize, actually, over the years, in order to get local permissions, regulatory permissions to build new parts of plant, they had to install a nature reserve. They had to declare that 70% of their land was a nature reserve. So, you know, when you look at it, you think this is going to be fine. And then you realize, well, actually, if I'm going to install any kind of hydrogen production here or decarbonize, I'm going to have to negotiate with the bird lovers. So you know, there's a bunch of things that are both very technical, but also, you know, environmental, that have an impact ultimately on what you're, you know, producing, that you don't necessarily think of till you get, you know, into, you roll your sleeve up and you start designing it. So this, for example, and I'm not going to spend too long on this one. So in the middle of the SOL 200 is the prototype electrolyser that we've built. To then be able to understand, so as I told you before, this electrolyser is taking waste heat and essentially using that instead of a part of the electrical energy. So then you need to design a heat recovery unit. And where in the lab it was happy, you know, people were happy to say, well, you get free heat and the equation works. Of course, when you get into the real world, nothing is for free. If there's a lesson to take away, nothing is for free. But not free in terms of you know, euros or dollars, but not free in terms of electricity either. Because somehow, you know, this is a waste stream. You know, the clue is in the title. You know, waste is something people were chucking away. It wasn't ever designed to be useful, lovely flow rate, you know, beautiful quality, very stable. It was a waste stream, so nobody cared what it looked like. So you have to, and you've got to bring it to the right place. You need an electrical fan to bring it to. You then need a heat exchanger. So you can think, well, it's going to cost me some capex. But if it's also costing you in terms of energy consumption, then you're pretty quickly asking yourself, am I wasting my time here? You know, thankfully we're not wasting our time, but it's, you know, you can't not include the whole story, if you like. And then equally the processing unit, well, if you want to, you know, make sure that your oxygen is you're in a safe environment where you're flushing your oxygen through, then you often have an air sweep through an electrolyser. So then you've got to, you know, you've got to have a processing unit, you've got to remove the nitrogen off. All of these things add up, and you do have to make sure you've looked, I guess, that you've taken your battery limits or the boundaries of your problem, you know, at the right level to be sure that you're having the impact you want, the impact you want in terms of energy efficiency, in terms of CO2 reduction, and of course, you know, in terms of cost. So yeah, over the last 3 years, we've built stacks, tested and tested and tested and tested them, and then you test them and you cross them out and you start to get, you know, you learn a lot. You learn a lot, and I think in that phase, you have to be prepared to try things, learn, and stop them and try something else. And that sounds easy to say. When you're charging that, it's not easy to do. You know, people get very attached to whatever it is they're doing. Understandably, people have put, you know, but if you think about the first thing I said, that this is a short timeline with enormous things to do, you know, one of the biggest things you learn in industry and technology development projects is the way that you go fast is also to be quite brutal about the things, you know, to start think, you know, but be brutal about killing this, you know, be bold about the sorts of things you try, but then be prepared to, you know, pivot and not keep chasing things that you think for whatever reason that aren't going to work. And we really did learn that around the different stacks, and we moved to different types of stacks. Getting a pilot line, actually getting the manufacturing people in from day one. You have a few big aha moments that the first day, as you can probably imagine, they looked at the first design and you say, well, actually this is never going to be manufacturable at scale. But get those learnings as early as you can. Don't wait 5 years of design time of whatever it is before you realize it's not manufacturable at the sort of scale. The only way your business can work is if you're at this sort of scale. The only way anybody's going to buy it if it's at this sort of scale. Then it's got to be manufacturable at the right price at this sort of scale. And the system engineering, as I talked about, so we're actually rolling your sleeve. You've got to roll your sleeves up and do it. You only really learn the things when you start to build that system, and when you start to try and put that contract in place with the person who you think might buy one of these things one day. You then really learn what the constraints are. So I'm going to wrap up. So I said, the task is enormous, the timeline is short, and that means you have to apply that throughout in all of your thinking. About how to get the right technology and accelerate. This is us in the steel plant a couple of weeks ago. That producing hydrogen, you need a decarbonized molecule for net zero. Clearly you do. Right now, worldwide, but Europe's about the same. Of the energy we consume, 20% of it is in the form of an electron. 80% of it is in the form of a molecule. So when you're thinking about decarbonisation, and I know you guys are all very familiar with this, but we're looking to double the really globally. Can we consume 40% of the energy that we consume in the form of an electron? Can we push it to 50%? All of this is difficult because doubling the size of the grid is almost impossible, or it's more than a 10-year project in most countries. Certainly this country it is, but it's not easy to economically and safe, produce hydrogen. It's doable in the same way, but you need to electrify absolutely everything you possibly can first. The more you look at producing hydrogen and producing that green molecule, which you need, absolutely you need something you can move around, but you do think just electrify everything. You push the boundaries of what you think you can electrify before you start thinking molecule. It's you've got to really push that up. And then I think, context is everything. It's what we learned, as I said, in the cement, in the steel. The regulatory context is everything. It changes the game. When Europe, Brussels came out with what they call RFMBO, it's a lovely Brussels term, but essentially, what is green? How am I going to define what green hydrogen is? It completely changed the game, and it needed to, but it completely redefined the projects that you could no longer capture CO2 from a cement plant, combine it with hydrogen, and sell it as a green fuel. So it changes. Your project is a no. So understanding the context, and I think you can't sit in conferences and understand the context. It's got to be actually getting to where the rubber hits the road and having conversations with the person on the other side of the table, the director of a steel plant that wants to decarbonize. He or she doesn't know how they want. They don't know. They don't have the answers. But the longer you spend talking to, and I don't mean it's just sort of, yes, chatting over coffee, but also what we did a lot of was whole systems modeling. And we've got a quote from the cement plant with us, this week doing that, where you actually, you're able to really roll those things up together and have conversations that are sort of model assisted, if you like, so that you're really working out what's going to work in the world in which you live. And I think that helps you to kill ideas that aren't going to work. But I think it also helps to have ideas. If you can manage to tease out what is the real problem, then you can also have ideas that are really going to have impact. Imagine the opportunity. I think what you see when you're working on the energy side is that, and a lot of you guys, I would put on maybe the demand side of how do people consume energy, how do buildings consume energy. A rethink of the demand side is a must. People can't consume energy and feedstocks the way they do today, and expect it to be cheaper. with a decarbonized molecule. You've got to rethink, which is about, reduction, it's about more efficiency, but also I think in terms of just the shape of demand as well, obviously. And then, one of the things that really came across to me through these projects, but also through the foundation and the conversations we have, the research that our women are doing across so many different, domains, almost all of which are being impacted by climate change, that you need to have very broad conversations to really understand the problem and to get beyond your comfort zone in understanding the problem, and defining it. And I would say that's, obviously in oil and gas, you've got to get beyond your comfort zone and understand, you've got to be quite humble and understand, the real problem that the emissions are creating. But I think it's also, I think of us in Kampala there a month ago. So, Uganda has just discovered large oil resources in a country that is low on the development index, a growing population. Not everybody has access to electricity, and there are some tough conversations to be. It's easy from London or Paris to say, well, those resources should stay in the ground. It's not so easy to have that conversation when you're in Kampala, and I think there's a lot of these difficult conversations that need to happen about, the way, because actually this is something you're talking about that is going to affect the way people live. It's going to affect what people do. And I get the sense that very often we shy away from these conversations. Wherever you sit, you shy away from the conversations. And I think what I've taken away is that if you want to understand the context, then you've got to be quite bold about stepping beyond. And I think the way you're setting up sort of interdisciplinary groups here also talks to that you do have to be talking, cross-discipline, cross-ideology, if you're actually going to, get things done. And I think also there's for scientists and engineers, I think there is a responsibility to be, quite courageous in being quite honest about what you see in the analytics, in the numbers, about climate change, about what you can do and you can't do, that there's and I see there's a sort of, we're all a bit bombarded by what people think about, expert opinions on things. But I think there is, an onus on scientists and engineers to be curious, to encourage people to take be they, undergraduates that you want to bring in, or, school children that you want to bring in, or others that will never have a career in science or engineering, to encourage people to take the time to understand. And then I think in the way in which we communicate, that we do so with both integrity, and hope, that I think is very important in whatever, field we're in. So those were my sort of takeaways from, sorry if I've run it a little bit over time. I don't know whether any of it speaks to you or whether there's things you'd rather I've said or talked about, but thank you for your attention.
So many aspects. I mean, this business of actually getting to it.
Yes.
If it works in theory, it might never work in practice.
And
so because we, at universities, you probably know, this is kind of where we struggle, isn't it? We're idea creators.
Yes.
We testers, ideas, and not necessarily worrying about, will this ever turn into a product in my hand in a certain amount of time. So that was actually a very salutary message that I took away in my own head. And the beauty of attending these talks is one never knows what one is going to learn. I mean, I didn't know there was 33 kilowatt hours of energies in a kilogram of hydrogen. I never thought about it that way. And sort of the question in the back of my mind is, you said 75% of the cost is electricity.
Yes.
In extracting
yes.
energy.
Yes.
So are you saying that actually you're only getting about 25% of that energy out of that kilogram? Is that, I mean, the cost
so I'm talking on the production side for the moment. So there is, you know, how do you then consume that kilogram of hydrogen, and what's your efficiency on the sort of fuel cell or the consumption or the, but you know, some of your challenges when you're talking about hydrogen, you are often talking about one, creating it by plugging energy into something and, you know, a reaction that consumes energy, and then you're potentially converting it back to electricity afterwards. So, you know, you have got to think quite broadly about it. So for my kilogram of hydrogen that has a, you know, has useful energy content of sort of 33 kilowatt hours or equivalent, if you take a current alkaline or PEM electrolyser, you're putting about 52 kilowatt hours of energy in to you know, to get that out. I should give it to you in sort of percentage electrical efficiency, but that you know, that's sort of magnitude. What solid oxide electrolyser producers think they can do is produce that kilogram with about 39 kilowatt hours of electricity. So potentially could make a big impact. However, my little caveat would be to say that most of that published work is at stack level in a lab, where it can be very convenient to not have necessarily thought of the whole story.
Yeah.
That said, I mean, you know, we're assuming that you are going to have to add some consumption to that, because you've got to get the heat to the electrolyser. You've got to but even if you're, you know, even if you have an electrical efficiency gain of 10%, that can be enormous. If 75% of your cost is your electricity, and you're talking about massive scale, then even that sort of gain is, you know, when you scale it up, is huge. And of course, it's not just in your OPEX, if you like. It's also, if you think that for this to be of any interest whatsoever, the electricity going in has got to be decarbonized, otherwise there is no point.
Yep.
So that means, and in, you know, the French would firmly believe that means nuclear, and are reasonably pragmatic about it. Brussels and Germany, that needs to be renewable. It needs to be wind or solar, and it needs to be additional wind or solar dedicated to that electrolyser, for understandable reasons. You can't rob Peter to pay Paul. You know, the first thing I said was electrify, electrify, electrify. Yeah. Well, don't start building lots of you know, renewable electricity, you know, wind or solar, and then say, oh no, actually I'm going to go and produce hydrogen with it. You know, that doesn't make sense. So you have got to, in order to do your green hydrogen project, you have to spend large amounts of capex to you know, to bring the renewable electricity. And if you're 10% more efficient or 20% more efficient, yes, lower operating, but also lower wind farm, you know, smaller wind farm that you need, and that talks to capex, it talks to the upper, so you know, it can be potentially a big game changer. But the but is, you have got to make sure you've understood the problem at the scale that you would be selling it. You know, that it goes beyond what you can. I mean, in a lab you can see, you know, sort of 30% potentially higher electrical efficiency, but it doesn't tell, you know, you have to get to the point that you've understood the whole story.
Yeah, so I mean, that's okay, so thank you, that was really illuminating. The other thought I had, sorry, I don't mean to, but hopefully people will chip in a second. The only other question I had was, you talked about demand as much as supply.
Yes.
Are you, is SLB working on the demand side of the problem, or is it mainly just supply side?
No, mainly supply side. It's what we've been in for, and I have to, and maybe this is the same in almost any part of the, you know, energy transition or transition technologies, that when you start to work on a particular bit, you think, oh, those guys over there must have it easier than I've got it here. I suspect everybody has it tough, but certainly, just as a sort of anecdote, I have 20 or so engineers in my systems engineering team that we all work in the same location in the tech center. I would say when we started with the project, about 5 out of the 20
cycle to work. Now there is only one who doesn't. Like, you know, when you start to realize how difficult it is and how expensive and how challenging to produce a decarbonized future fuel, well, you pretty quickly decide, okay, I'm just going to not use so much fuel, you know. We're not doing much in the demand side, but the more you look at how tough supply is, the more you think, please, 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 you folk working on demand technologies, you know, let's be as smart as we can about what we use.
So for what it's worth, so I mean, just quickly respond to that. I mean, how easy and how hard.
Yes.
A colleague of mine worked out. I don't know if you must have passed by the management building, the big glass block.
Yes, I know.
Yes, campus. That's got the same heat loss as a Victorian dwelling.
Yeah.
So that's about the progress we've made.
Yes.
In 120 years.
Of
building technology.
Yeah.
Okay. So, you know.
And I don't know, when was that built? Probably,
just
20 years ago.
3 years.
Oh, wow. Okay. Oh, gosh. No, that is,
So it's 2020s technology.
Yes.
With the same heat loss characteristic as a Victorian semi or something. So we kind of run into these sociological, socioeconomic problems about why somebody wants an enormous glass house.
Yes.
Which is actually the problem. The problem is there's too much glass in it, and glass is a very poor insulator.
And decarbonize it. So we've had a look at a few glass plants to decarbonize the manufacture of glass, and that's not easy.
So just in case you're wondering. On the one hand, demand side is, in that sense, you know, there's some easy. You can see the pathway.
Yes.
But actually getting to people to walk on the path.
Well, I think this is where it comes to the tough conversations. Yes. You know, certainly where I'm living in France, there has been a political expectation that's being set that you can have a decarbonized fuel. It's going to be cheaper. It's going to bring jobs. You can consume as much as you like, you know, and that, you know, this sort of panacea, that it's very hard, you know, when you're working in the reality, it's very hard to see how that works. You know, as we did, you know, people talk about previous energy transitions. You know, we went from burning wood to burning coal to burning oil, etc. Each one of those steps, you were going to something that was more energy dense and cheaper. This is not that step. This is a step to something that is less energy dense and more expensive. And we, you know, solar panels are cheap, you know, things that can, obviously you can scale them up, bring the cost down. But if you think just about the cost of the solar panels, or the fact that, you know, people sell wind turbines, make no margins in them, you know, you can tell a story where it all looks cheaper, but you have a grid that, you know, that somehow you've got to factor in the fact that your grid has got to be ready. You need storage, so, you know, ultimately, we're sort of, for the moment, we're sort of comfortable with telling a story where you can have your cake and eat it and consume more and more, and you really don't have to change the way you know, the glass in your buildings or the way you like
free lunch.
But there is no such, which, you know, at some point in time, we all need to be courageous enough to sort of have those conversations. And you know, you put 2 centimes on the cost of a litre of petrol in France, and people are out on the street. So it's politically just very, you know, very difficult to have the conversation. But if all of us shy away from the conversation all the time, well, we're not going to get it done in 2.5 decades. You know,
In the way I see it, the transition is going to be cheaper. Because if we count in the cost connected with dealing with climate change, at the end of the day,
absolutely. As soon as you embed the carbon, you know, the cost of, then absolutely. The challenge is then, you know, how do you embed that into the price that people? I mean, I think the one at the moment that I keep thinking about is AI. You know, right now you can go to, you know, you go to ChatGPT, you ask the questions, and you search, you know, aimlessly in all directions, and it whirs away, and you get an answer that you could pretty much have got from Google. You know, I mean, you know, I'm messing around with it. I'm sure you guys are doing smarter things with it. But the data center at the back, you know, has just consumed 25 times as much energy, and you're not being charged for it. is the, so we ought to be able to sort this out. But if you're not being charged for the fact that it costs in energy terms, which is pretty quickly dollar terms and CO2 terms, 25 times more to have done the same, query, then you would start to, things would naturally, but for the moment, those things are not embedded. So and different people pay. So I don't know what the solution is, but it's yes, if you really manage to put the dollars on the other side of the equation in terms of the cost of these impacts, but the future impacts, and it's always very difficult for people to evaluate future impacts that aren't going to impact them. I spent 3 years at the IEA looking at scenario planning in energy, and you learn from the economists. You go in there thinking, well, people will, they'll see the vision, they'll change their, and they go, no. Yeah. The only thing that changes behavior anywhere you are in the world, in any culture, is what hits their pocket. The bottom line is that's the way humans behave, so you do have to work out how do you
that's why we
make it hit people's pockets. And,
at the end of the day, that's why we are doing it.
Yes,
we can sugarcoat it as much as we want, but we want to do transition because it's more expensive for us to deal with the consequences.
Yeah.
So that's the only way of. There isn't a choice in reality.
But the problem is, we've been trying to write with Manchester, I don't know if you told you, generative design and engineering. And so I was sort of thinking about this issue, about why we as a society, as a culture, as a species have not been very successful in some things, where we can see a societal good, but it's a long-term good. So I know that the heat wave, it's just touched 52 Celsius in Delhi today.
Yeah. Gosh.
Which is the highest ever recorded, I think, in all of India at some point. I just got a text message. So you can see this future unfolding, but it is at some point in the future, right? So it's a funny thing, whereas as a species, we have what's called a long childhood. Yeah. It takes us 18 years to mature an adult in the species.
Yes, right? Yes.
So we understand this as a parent. I know that my son is now 13. He's got X number of years. I'm going to have to put in all that work to make sure he turns into a good citizen. Blah blah blah. But as a society, somehow you flip the lens to a collection of individuals, per species, and suddenly we can't work.
And we are outliers in that species.
And we are the outliers.
We've all got sort of engineering degrees. We're real outliers.
And so we can't seem to work for a collective good. So this idea of long childhood at a species level, it doesn't seem to be happening. At a cultural level, it doesn't seem to be happening. So it's a strange dichotomy.
It is.
We understand that some things take time, and the payout is much later. But for other things, if it's not free, I can't, sorry, I'm not using it. If I can't do
and if it's not getting me elected on July the 4th, then
exactly. So it's
it's
challenge.
Yeah, none of it's easy. Yes.
We're lucky that we haven't been out yet. I'm guessing there will be another contact meeting.
Yeah.
Just if we have questions or comments, because otherwise we'll make it down before our questions.
No, thank you.
Anthony, anybody else? Okay, awesome. Well, thank
you.
Oh, that was really breaking the party. I'm sorry. Online people, any questions from online comments?
Oh, yeah. Anna,
Tasha and Nick. Is anyone online would like to contribute before we? I did really good.
Well, thanks for joining online anyway.
Say
bye-bye.
But I'm worried that we might make it out in 15 minutes. Okay, thank you online.
No, thank you for your attention, everybody. Thank you.
Yeah, sorry, I wasn't chatting with anybody on the phone. I was taking notes.
No, you're welcome. You learn a lot when you roll your sleeves up and actually try and do stuff. Yeah, and then you sort of try and think, okay, how do you now apply what you've learned? But
So that's why
there's more urgency than people realise. No. Yeah.
better multiples of better than the best is.
Yes.
So let's imagine this new thing you've discovered. There's something must have been doing the job of that thing, and you
Yes.
invented the best thing, best version of that. Well, it better be twice as.
Yes, and you tend to be measuring that good on a given axis.
Yeah.
Well, it also has to be safe. It can't blow. You know, there will be showstoppers.
Exactly. So by the time you really